Hello, my name is Sullivan Meneghetti, and I am here today to present to you my science fair project, Building a Bioplastic for the Future, an examination into the strength of starch-based bioplastics. Now, this whole idea came about as I had the thought. As the supply of non-renewable petroleum-based plastics dwindle, will bio-based plastics be a viable alternative for the future? Now, this whole experiment explores the idea of making bioplastics out of starch. Now, starch contains polysaccharides. Polysaccharides are simply large sugar molecules. These large sugar molecules are extremely efficient for making bioplastics out of. Now, the sugars that make up these polysaccharides are amylose and amylopectin. We will be focusing mostly on the amylose content. Now, let me go. The hypothesis for this general experiment is if a bio-based plastic contains higher levels of polysaccharide amylose, then the force at the break, or the tensile strength, will increase. Now, let me go over my experimental design. My independent variable was each type of starch used. I used 4 different types of starches. I used corn starch, I used amioca starch, I used hyaline starch, and I used pea starch. The first 3 I just mentioned are all cornstarch or are GMOs of cornstarch. Now, our control group is going to be amioca, as it has less than 1% of amylose, and that will tell us what it's like if we have almost no amylose. Our dependent variable is going to be the force at the break when the sample snaps, essentially. Everything else is our constants and our materials. Now, let me go over my procedure with you. First, you're going to collect the supplies, then you're going to take a 1/4 cup of starch, then you are going to take a 1/4 cup of water, and you're going to take a 1/4 teaspoon of glycerol. You're going to mix that together, put it in the microwave for 30 seconds, pull it out, let it cool overnight. Then you're going to take it out, cut it up into evenly sized strips, and pull it apart on our force gauge, which is seen here. And I would like to thank Smithers Oasis Laboratory for supplying the force gauge, and I would like to thank Ingredion for supplying the starches. Now, we did 10 trials for each starch, essentially meaning we made 10 different small samples, and we pulled each apart, and we measured the force. Now, let me show you our spreadsheet with the averages. Now, amioca starch took 1 Newton to break. It had less than 1% amylose. Cornstarch with 25% amylose took 11.6 newtons to break. Pea starch with 22.6 newtons to break. It had 40% amylose. And the hyaline starch with 55 took 8 newtons. Now, I was taken back by this, as according to our hypothesis, if bio-based plastic has a higher level of polysaccharide amylose, then the force at the break will be higher. Hyaline should have the highest force at break. And if we look at our chart here, you can see it continues to go up until it gets to hyaline. So I went to some experts. I went to Dr. Paul Kelly, the head of polymer sciences at Smithers Oasis, Heidi Wang, the technical manager of Ingredion, and Dr. Paolo Meneghetti, the head of research and development at Smithers Oasis. Now, they suggested that there could be a sweet spot for the amylose to amylopectin, and we believe that hyaline exceeded this, thus resulting in it getting a very low tensile strength. So, in conclusion, though, our results were supported by 75% of our data, thus proving the hypothesis that if a bio-based plastic contains higher levels of polysaccharide amylose, then the force at the break will be higher. This was proven correct. Now, why would this affect our everyday lives? Well, if we can apply this to most every single field. We can apply this from toys to medicine, especially medicine. If you take any single medical equipment, it needs to be disposable. Syringes, gloves, like tubes, all sorts of different things. And this plastic is very easily disposable, as it is a plant-based plastic and will degrade fast enough. And if we can make sure that this plastic soon becomes water resistant, then all different types of uses for this plastic will become available, and we can replace almost entirely regular petroleum plastics. One thing I would like to note here, when discussing with Heidi Wang why pea starch might have gotten such a high result, she suggested that there could have been a protein inside of it that could have caused it to get such a high result. So if I was to do this again, I would try to see if that was any kind of variable. As I said, all of the other starches are related to corn, so that variable wasn't involved in those. However, again, our result was proven correct, that if a bioplastic plastic contains higher levels of polysaccharide amylose, then the force of the break will be higher. And I thank you now for taking your time and your energy to look at my science fair project and consider it for the science fair. Thank you.